So on the cryptographic side, the coolest improvement that was made was actually switching from a hash to a commitment. And instead of just adding a private salt, we actually used the Pedersen commitment to get perfect hiding. So that's been replaced. If you look at the code for it, it's actually kind of simple initially. The issue really came from, aside from kind of working from scratch on it, having to generate the fixed bases. Not a very difficult thing once you know the API. It just took a little bit of time to figure out. So we actually have a separate repository which kind of isolates the work that we did figuring this out. So basically it came down to reversing what was done in the orchard circuit. And again, the hardest part of this really was where they were using find Z's and U's. So, and this is all commented out because again, this is kind of a garbage code base that we just did one and done. Use the Palace point hash to curve API, which basically gives us a domain separator for what we're trying to commit to. And then we take the points, marshal them into whatever we need them as. And then this is a very low-tech solution. Again, why a lot of this is coded or commented out. We literally just print it, and then we put it in some formatter. And once we actually have those values, it's really pretty easy. Again, this was pretty much formatted for us. So Z is the blinding factor, which means it's big, and this is like a full width scalar, I believe. And then there's also the binding factor, and so since we're using a 128-bit, not even, we're using a 100-bit value for our board, we can easily fit that inside of a short scalar. So we go ahead and actually we take advantage of that. And then we do the proper tests as actually appear in Orchard. But as you can see, this is the same exact code. The same tests show up here in our actual BattleZips-Halo2 code base. So how we actually generated the Pedersen values is handled by this repository a little more. We didn't put the utilities in here. The other thing that we wanted to do was actually use this in the browser, and beyond the actual usability, which we'll get to in a second, there were some issues getting the code to compile to a WASM target, and this definitely came from an unfamiliarity with trying to do what we were doing. So essentially the issue was that we had in our binary utility, which it was using an array of 4 64-bit integers, and if you know WASM at all, you know that currently it's only a 32-bit virtual machine. So what we did is convert it to binary buffers. So that took a little bit of R&D. Originally we were trying to figure out if we could just do some mindless magic and pull someone else's solution, but eventually we just figured out what was going on. So once we did, we were able to convert everything just again to be from U64 to U8, and that would actually allow us to compile to our WASM target. So the actual WASM, the library that we export itself, is pretty simple, to be honest. We used a little bit of inspiration from Zordle, which basically just passes in the, there's a tuple of 5 ships, and then each one is a tuple of a U8, and a bool. That's how you basically configure your board. So that's what comes in. It does what's done in the production proof it, and just marshals it back out, and then this same kind of thing is done if you want to verify it again. So we can actually go compile it by running, and then we can actually find the artifacts of building this, which we'll then go use in the front end. I think there are actually a couple of steps here that I'm missing with WASM pack, but that's pretty simple for anything that you're just doing like binding Rust to JavaScript and WebAssembly. All that should work exactly the same. But in the actual front end, we have these artifacts, which again we have right here. So as we'll see in a second, this is a very, very simple test of what we're trying to do, and we'll get into why we didn't go further with it. We've actually seen how it performs. As you can see, the performance on this is pretty abysmal. We can do much better with Circom and R1CS. So, and that's clearly like not how Halo should be going. So it's something, or many things that we've done here are incorrect, but we need to definitely figure out how that works and get a little more intermediate in how we're approaching this. So there are a lot of reasons why we might want to use the KZG fork. It seems like there's a big reason for like the snark verifier package or for accumulation. To be honest, we probably want to just spend more time digging directly into exactly what's going on there. I actually started trying to implement the KZG fork right before ZK hack. We got through some of it once it was clear that we had to completely get rid of Palace to have it perform correctly. We didn't really have the means to rewrite all of the stuff that used like the EC math and everything. So we ended up just putting it down and doing a brand new project, just also in the spirit of a hackathon rather than that. Other repository is actually BattleZips-Halo2, where we built something that is probably highly under constrained, but technically did use PCD recursion to accomplish. Specifically, we showed off a ZK state channel, and it was pretty slow. It had a lot of problems, but we did kind of prove the concept to ourselves, which was pretty awesome, actually. But while we still think the mechanism of having PCD recursion passing these proofs back and forth is useful for some kind of asynchronous operations, the use case that we've chosen, battleships, which is turn-based and very much incrementally verifiable as the same move over and over, we were essentially kind of given the feedback that we maybe overlooked accumulation as the proper way to handle what we're trying to do with state channels in something like Halo 2, which means that we do just want to generate many of these proofs over time without doing any sort of recursion, and then doing a final accumulation of all of those. So all that said, there's still a lot of stuff just within Halo 2 that we really think we should be understanding. Again, KZG, and then there's like the Halo 2 wrong, there's the snark verifier, all of these things which are native with the KZG fork. So I think that this is definitely something that eventually, like the battleships demo, can be expanded on, but given the performance that we saw in the front end when we put it in, I think in summary, we just need to try to get a little more familiar with what's going on with Halo 2, Plonkish, arithmetization, all that stuff. But in general, I think so far the project has been a really good success. We've put a lot of really novel code out there that should be useful for people who have no clue how to use Halo, and we'll definitely be trying to take another stab at it once we're a little more strategic with how we can write our code rather than just trying to get anything and everything to work.